Let's use the heat mass transfer analogy to derive and explain the Lewis relation. So we want to try to relate our heat transfer coefficient to our mass transfer coefficient. This is going to be the key principle in deriving this equation. And we want to use the Buckingham Pi method equations for both heat and mass transfer. So there's unitless variables like the Sherwood and the Schmidt equation for mass transfer that can help us determine the Lewis relation. So if we have mass transfer, and for mass transfer, ooh, I'm sleepy. For mass transfer, we have our Sherwood equation, which is equal to our heat mass transfer coefficient multiplied by the length of the area that we're trying to solve for, divided by the diffusivity coefficient of A to B. And then we have our Schmidt equation, which is equal to the viscosity divided by density multiplied by the diffusivity coefficient of A to B. And then for heat transfer, we have analogous equations that relate back to the Sherwood and the Schmidt equations. We have the Nusselt number, which is equivalent to our heat transfer coefficient multiplied by the length divided by our our thermal conductivity. And then we have our Prandtl number, whatever, which is equal to our heat capacity multiplied by viscosity divided by our thermal conductivity. You can put these equations into simpler terms. This Sherwood equation is simply the convective mass transfer, I'm just gonna call that MT, divided by the diffusive mass transfer. For the Schmidt number, we have our momentum, diffusivity, and I'll just put capital D, divided by our mass transfer, MT, diffusivity, D. These aren't actual acronyms. I'm just simplifying it down. And then for our Nusselt number, this is also convective, but instead, this is heat transfer divided by conductive, thermal conductivity, heat transfer. This is our Prandtl number is equivalent to our momentum, diffusivity, D, divided by our thermal diffusivity. So of course, from here, we want to relate these equations back into finding our Lewis relation. And this is the analogy we're talking about with heat and mass transfer, right? We have our Sherwood and our Nusselt number, which are essentially the same idea, just with mass versus heat, and our Schmidt versus our Prandtl number. So we can create a ratio between our Sherwood and our Nusselt number because we want to make a relation between our heat transfer coefficient and our mass transfer coefficient. And both our Sherwood and our Nusselt number have those two variables. So we take our Sherwood divided by our Nusselt number, and we get, let's see, flip that around, our length goes away, and we just have our mass transfer coefficient multiplied by the thermal conductivity divided by our diffusive coefficient. Yeah. Divided by our right? And our heat transfer coefficient. My bad. So we can relate this to the Schmidt and the Prandtl number. In some studies, they proved that the Schmidt and the Schmidt and the Sherwood number can be related back to each other, and the Nuzelt and the Prandtl number can be related back to each other as well in a different equation. And that equation is the Sherwood number is equal to the concentration multiplied by the Reynolds number to the 1/2 power multiplied by the Schmidt number to the 1/3 power. And you can imagine that this is essentially the same for our heat transfer. Our Nuzelt number is equal to concentration Reynolds number to the 1/2 power multiplied by the Prandtl number to the 1/3 power, which means that our relationship is also equal to the Schmidt number divided by the Prandtl number to the 1/3 power. So if we write that out using its variables, we get what? Okay, so our viscosities cancel out. Is that it? Thermal conductivity on top and a lot of variables on the bottom. Yep, so that's it. So our thermal conductivity is on top divided by our density, heat capacity, and our diffusive coefficient. So 8 to the e to the 1/3 power. This is our Lewis number. And it does not have any units. It's unitless. This is also our Lewis number, of course. And when you substitute in the water vapor variables into this equation, you get somewhat the number 1. And that will be important in a few seconds. Because what we're going to do is we're going to relate this equation to our Lewis number to this equation. And so we're going to label, instead of it being the Schmidt number over the Prandtl number, it's just going to be LE, right? Lewis. So we have our mass transfer coefficient multiplied by our thermal conductivity divided by our diffusive coefficient multiplied by our heat transfer coefficient is equal to the Lewis number to the 1/3 power. And that's equal to our thermal conductivity divided by our density, heat capacity, and diffusivity coefficient to the 1/3. Here. Now if we substitute in the Lewis equation to here, and we divide some of these numbers out, we can cancel out these two thermal conductivities. I'm dividing it out, right? Okay, so then these two numbers can go away. So it should just be our ratio between our heat transfer and our mass transfer coefficient multiplied by our density, heat capacity, and our Lewis number. And that is equal to our Lewis number. But remember, our Lewis number to the 1/3 power is equivalent to 1, like we said earlier. So we're just going to call that 1. And we're going to multiply our heat transfer coefficient over. And so now we have our heat transfer coefficient and divide. Well, before we multiply our heat transfer coefficient over, we divide by our Lewis number. And so we get our heat transfer coefficient is equivalent to our mass transfer coefficient multiplied by our density and our heat capacity. And this is the Lewis relation. This relation is a wonderful tool in helping relate mass transfer to heat transfer. whenever you're trying to solve for mass transfer, heat transfer, and then if you have variables with mass transfer, you're able to solve for some variables with heat transfer and vice versa, right? Because you can switch around your equation and get that our mass transfer coefficient is equal to heat transfer coefficient divided by our density and heat capacity. And so this helps you relate these two separate topics together. So now that we've derived the Lewis relation, we're going to do essentially an example problem where we're going to create a relationship between wet bulb temperature and adiabatic saturation temperature, and from there derive an expression to understand the molar concentration of water in terms of the dry bulb or wet bulb temperature. So that sounds confusing, right? That's a lot of what does that mean? Let's come over here and let's draw out the situation. After determining and deriving the Lewis relation, from here we're going to do an example of creating a relationship between a wet bulb temperature and an absorption saturation temperature using the Lewis relation, of course, as well as eventually after that we're going to derive an expression for the molar concentration of air in terms of dry and wet bulb. So let's start by drawing a wet bulb and then draw an absorption saturation temperature. Yeah. Whatever, you get the idea. So starting with our wet bulb. Not a light bulb. I made that mistake too. I thought we were talking about light bulbs. Please be straight. Whatever. It's not. We have our liquid, temperature W, and concentration W. Above we have our air flowing, air with temperature air, and our concentration goes to infinity. Infinity. And in this problem, we have our heat being transferred into the bulb. Because heat's being transferred into the bulb, we need mass transfer, so our moles of water are being transferred out of the bulb. This is a wet bulb. Wet bulb. Wow, very interesting. Because of that relationship, we are at steady state. So we can relate our heat and mass transfer equations to each other, set them equal to each other, and then use the Lewis relation to simplify down the equations and create a true relationship. Start with let's do our let's do our heat transfer. I've decided heat transfer. Heat. So we have our heat transfer coefficient, our area, our temperature of the air, minus the temperature of the water. And that's it. And this is in joules per second. Then we have our mass transfer, which is our mass transfer coefficient multiplied by the area multiplied by the concentration of the water minus the concentration to infinity. It's basically a concentration of the air. This is in moles per second. That's no bueno. How are we going to set these equal to one another if that's moles? Great question. We're going to use the enthalpy of vaporization. Add that on to the end of this equation just to convert those moles into joules. So now we can set these two equations equal to one another and use our Lewis relation, which is the fact that our heat transfer coefficient equals our mass transfer coefficient multiplied by density and heat capacity. So let's just plug in the Lewis relation already so I don't have to cancel everything out. So we're going to plug in the Lewis relation right here. And that's going to be our mass transfer coefficient multiplied by our density and heat capacity multiplied by the temperature of the air minus the temperature of the water. And we don't have to plug that into our mass equation based on Fourier's law. Like this is Fourier's law. Because we have the variable we want, right? We have the mass transfer coefficient. So we have our mass transfer coefficient, our area. Oh, we forgot the area here. It's okay, we're going to cancel that out in a second anyways. And our lambda. So let's cancel out our area and our mass transfer coefficient. And what we're left with is our density, heat capacity, temperatures, difference in temperatures, as well as our difference in concentrations, and our lambda, which is our enthalpy of vaporization. So there you go. We create a relationship between the two, right? And it's just setting the heat equation equal to the mass equation, and then plugging in the Lewis relation in order to cancel out any variables that we don't want anymore. So that's the wet bulb. Let's do the adiabatic saturation. I've been calling it adiabatic saturation and not something else. So with adiabatic saturation, we have the water. I'm under the water. Help me, I'm under the water. With our temperature of the water, 1, because when it comes out, it's going to have a different temperature. It's going to be temperature 2. And then we have the temperature of the air, 1. No. The temperature of the air, 2. Now the concentration of the water is equal to 100%. Why? Because it's saturated. I mean, that's the answer. Saturated. It's relative humidity. Because of this, we know that our temperature of the air and the temperature of the water are equivalent at this end. And because the temperature decreases, right, it must decrease, and the molar concentration increases, we can determine that we can also set the heat and mass equations equal to one another once again. So we'll do the heat equation, and that's going to be our heat transfer coefficient. It's the same equation, but area, but instead of the air minus the temperature of the water, it's still going to be that, but it's going to be the temperature of the air, 1, minus the temperature of the water, 2. And our mass, don't know why I forgot that word. It's late. It's not that late. I'm lying. Is our mass transfer coefficient. It's 8. It's not that late. It's like medium late. Mass transfer coefficient area multiplied by the concentration of the air, 2, right after, minus the concentration of the air, 1. So again, plug in that Lewis relation, right? We know that Lewis relation by now. Plug that in and set these equal to each other. We're going to plug it in again for our heat transfer coefficient. And so we get mass transfer coefficient, density, heat capacity. Wait, before we do that, remember, you probably caught this. This is in joules per second. This is in moles per second. Add that enthalpy of vaporization. We're good now. Okay, so now let's plug that Lewis relation in. And we get mass transfer, density, heat capacity, temperature of the air, minus temperature of the water. It's equal to mass transfer, area, concentration, lambda. Cancel things out. The areas here, but it's getting canceled out anyways. Density, heat capacity. Oh, let me get pink. Density, heat capacity, temperature of the air minus temperature of the water equals concentration of the air minus concentration of the air, but earlier, and lambda. Great. Right, so now we have these two equations. We have our equation for our wet bulb and our adiabatic saturation. Let's pull these guys together. Come here, guys. Come here. Come here. I'll label them so you know which one's which. So this, oh, this is the wet bulb, WB, and this is the adiabatic saturation, AS. The relationship between our wet bulb and our adiabatic saturation. Now we're going to create an expression for the molar concentration of, is it air? Yeah, I think it's air in terms of a wet bulb and a dry bulb. What we can do is we understand, or you should understand, that this concentration is 100%. And this relative humidity is 100%. So what we're going to do is we're just going to plug that in to our unknown values, right? Right? This one, it's this one, right? Plug that in for our unknown values and then create an equation. So we have our concentration of our air 2 minus our concentration of our air as well. Infinity is basically air. And that's equal to the density, heat capacity, multiplied by the temperature of the air minus the temperature of the water, divided by lambda. So for our wet bulb, all we're going to do is add over concentration of our air. And that, because this is, right, this is 100% concentration. So that's going to be wet. It's wet, right? Versus this concentration is 100% air, so it's going to be completely dry. So for our wet bulb, we'll use that as a variable, and we'll have concentration of our air minus density, heat capacity, temperature of the air minus temperature of the water divided by lambda. And it's just the opposite for dry, right? Our variable is concentration infinity equals, should be added. Concentration infinity is the concentration of our air minus our density, heat capacity, temperature of the air divided by lambda. And there we go. So we just discovered how to find the relationship between a wet bulb and an adiabatic saturation temperature, and then use that to derive an expression to find the molar concentration of air in terms of a dry bulb and a wet bulb. Look at that. See, that's molar concentration of air in a dry bulb and a wet bulb, as well as our Lewis relation. Look at that. That's our Lewis relationship.